I'm very happy to be here. I'd like to thank David for kind invitation to attend this event. I'm Chun Zhang. I think what I like to talk about is quite recently discovered a new high TC superconductor in the Nickelate. So that's the outline of my talk. First, I will give an introduction to the Nickelate superconductivity. Then we'll discuss molecular mode insulator in a two-layer covered model, filling 1 quarter per side. Then I will discuss the self-doped molecular mode insulator and discuss the electronic structure of this material and the high pressure, and argue that the basic electronic structure of this may be described by a self-doped molecular mode insulator. So these are my collaborators, Zhang Wang, postdoc in Boston College, a former student in Kavli Institute, and Zhang and Zhang Hu from IOP, Chinese Academy of Sciences, and Zhang Wang at Boston College. And part of the work has been published in Chinese Physical Letters, and the main part of the talk were still in the preparation and writing. So what I like to discuss the Nickelate is to try to compare with the more well-known cuprate superconductivity. So this is so in the first introduction, I want to discuss the ITC cuprate. Okay, that was discovered a long time ago in late of 1986. So what I show you here is one of the compound, the lantern strontium copper 04. Okay, this is the main message. It's the main part of this is described by copper 02 plane. That's it. And so that's the copper 02 plane. And this is the phase diagram of the cuprate. So if I have this, use this X, that means the chemical doping. And without the doping for this compound, that means there's no strontium here. So this is a well-defined antiferromagnet. Then if you apply chemical doping to introduce X, okay, here, then gradually you find the D-wave superconductivity. And the high TC for this is 40. The highest TC for cuprate is not. It's over 100 counts. Remains to be the highest transition temperature superconductor and the normal pressure. And there are some other normal phenomena like sugar gas phase, strain in metal, or these kind of relative quantum phenomena, quantum critical point. But what the main focus is today I want to try to emphasize is just to see the similarity and the difference between Nickelate and this cuprate. So this is the plane I mentioned. The main physics is coming from copper 02 plane. Okay, so this is so if I look at this compound, then the copper is 2+. That means you have 3d9 electron or 1d hole on this dx squared minus y squared compound. Okay. So this is oxygen and this is the copper. So the model without the doping is well described by spin 1/2 Heisenberg model in square lattice, which has been studied both experiment and the theory very well, and with excellent consistency between theory and experiment. So doping is more interesting, but also more complicated. So if I dope introduce some additional hole on this copper 02 plane, so finally you need so-called doped Hubbard model or TJ model. The J is just the spin-spin coupling. T is just the nearest neighbor hopping, but with some constraint. That means I allow only one electron, let's say, per site. You cannot put 2 electrons on the site. And there are a lot of discussions and study on this, the TJ model, although it's still not conclusive, but most people believe that the model contains some essential part of high TG cuprate. So to look at the nickelate, so we consider similarity with this cuprate. That means I have 1 electron or 1 hole per site to start with, which is spin 1/2. Okay. So actually, soon after discovery of cuprate, there are questions raised. What about the other compound and the nickelate in particular? Because the nickel is just next to copper in periodic table. So for instance, are there other planned half systems with a large value of T and J? So you would expect a large high TC, okay, and whether it's a nickelate. And the favored valence of nickelate actually is 2+. But the nickel 2+ is a spin 1 instead of spin 1/2. So that is not good for superconductivity, okay, and difficult to be doped, okay, and because also Hung throughput is important. So the question about the nickelate is, can we force a different nickel valence with spin equal to 1/2? Okay. Actually, this is very rare and is planned for ordination. Okay, but this was actually studied many years ago, and as I learned, this Muir and Bernos have actually searched for superconducting nickel. They did not find it, but they found it instead in cuprate. And then Marshall Weiss and Anisimov and their collaborator predict the possible superconductivity in the 112 phase of the nickelate in about 25 years ago. Okay. And many groups work on nickelate. However, the superconductivity in nickelate was not found until Harold Hwang's group in Stanford, okay, found 15 Kelvin superconductivity in this thin film. Okay. So this is just the energy level for the copper 2+ and the nickel 1+. So you have 1 spin, okay, 1 spin 1/2, that's 1 spin 1/2 hole on the dx² minus y² level. That makes these carriers to be spin 1/2 and possibly superconductor. That way. So that slide is to show what Harold Hwang's group discovered. Okay, we call the nickel age of a superconductor. And they discovered that in 2019. So what you need to know is this is an infinite layer, just 1 layer nickel O2. Okay, and the sample is not as good as the cuprate, but they do find a similarity. For instance, in this phase diagram, okay, similar to the cuprate, and that is the measurement, okay, for the resistivity function temperature for this neodymium nickel O2 and 20% doped with strontium. So that is clear superconductivity. So I think we have pretty good understanding about this nickelate, infinity layer nickelate. Okay. So this cartoon just show you, I think many other people, they have the similar theory about that. Okay. So what happens is this is a nickel 1+, okay, and then there's a self-doping because this neodymium, okay, or lanthanum, actually they will have some electrons. So for the undoped system, you have some holons and you have some kind of doublons. But then you further doping. Okay, that means to repress some of the neodymium by strunting, you introduce more such kind of holes. So that led to the superconductivity. And most, I think, experiments show that the physics of this or the electronic structure of this is similar to the electron dope cuprate. And the pairing of this is also D-wave, similar to cuprate. Okay. So below I shall discuss more recently discovered is lanthanum 3 nickel 207 under high pressure. So that was discovered last year by this Hwang's group and his collaborators. So this is the crystal structure. So different from the usual cuprate, now you have a double layer structure. So these the blue ones are the nickel. Okay, you have oxygen, 6 oxygen around, but this oxygen is shared by these 2 nickel. So that makes things very different. And about the superconductivity, initially the resistance was not found, but later I think it was confirmed by Yuan's group in Zhang University about zero resistance. The other thing is this superconductivity was only found under high pressure, about 14 to 15 GPa. Okay, and there's a structure transition as function of pressure increase. So this is a lower pressure phase, and this is a high pressure. As you see, at the high pressure phase, there's more symmetry. Okay, so this is the crystal tilt, and that shows more precise zero resistance. About a week ago, the clear evidence for the bulk superconductivity in this poly lanthanum 2 PR nickel 207 was reported. Okay, so that settled down that the compound is well-defined bulk superconductor in both resistance and also in its Meissner effect. So this, I think, experiment group also show that this the reason why this is good because stabilize the structure of the double layer structure. Otherwise, you have some kind of other 1-3-1-3 and the 2-2-2-2 structure. So that is a brief summary of the current status of this 2-layer Nickelate superconductivity. Okay, it's TC, it's up to 80 Kelvin. So that's above the nitrogen, liquid nitrogen temperature. Okay, and zero resistance and Meissner effect also confirmed. And of course, the question remains whether the high pressure could be replaced by other techniques, chemical doping or something. Okay, to control superconductivity by other methods, such as chemical doping. And of course, remains to be problem because such a high pressure, we don't have many experiments except the transport experiment. But people are thinking about the possible optical measurement. So what I want to do below is just to consider an electronic structure, the basic model, minimum model, and try to address the similarity and difference of these in comparison with the cuprate. Okay, so because this is the cup, if I look at this nickel valence, then nickel valence in this compound is 2.5 plus. It's away from nickel 1 plus. So that means looks like very different from cuprate. However, on the other hand, the double layer structure suggests importance of bonding between the two layers. Okay, so that brings us to study two-layer Hubbard model. Okay, and that also suggested from this band calculation method. So that this is the band calculation. Okay, so these two are different methods. I think this one is probably more advanced technique. Takes a much longer time. And so this is a lower pressure phase. This is high pressure phase. Let's look at the high pressure phase. Okay. So I have a 4-band here, you can see. So that describe two other symmetric and the two are anti-symmetric. Okay. It's a combination of the dx squared minus y squared and the dc squared. So that means double this layer structure gives you bonding and anti-bonding splitting of these bands, which are important. So that just led us to study this two-layer Hubbard model. So right now I want to focus on simple model. Okay. So this is a two-layer Hubbard model. It's a standard. I have a kinetic energy part and the cooling interaction on site. That means I put 2 electrons on the same side of this double layer system called the U, and I will consider U to be large. And this is just the 2 by 2, okay. And the kinetic energy is just given by this, and I consider eta to be the hopping between these two, and in the limit eta to be large, I have a very strong band splitting. So that the kinetic energy part, the energy of this HK can be written very easily. Okay, just it's plus minus eta. Okay. But if eta is large, let's consider this case. So we have a 2-band. Okay. So this is the bonding band. This is the anti-bonding band. And if this band splitting is large, if I consider 1 electron, let's say, if I consider 40 electron in average per side in the double layer system, then I can forget about this the anti-bond. Okay, focusing on this. Of course, because of the cooling interaction, you cannot put the electron just freely here. But I can drop all this because this becomes irrelevant. Okay. So if I have U also large, then we have so-called molecular multi-insulate. So every molecule, which I define to be just the 2 sides, one on top and one on bottom layer, okay, that will form a bonding state. And this is a singly occupied. So means the bonding state will be singly occupied. So that is described by spin 1/2 Heisman model. Okay, that's we call the molecular multi-insulate. Note that here just usually multi-insulate I have 1 electron per side. Here I have 1 molecule per side. Okay. So here, each side hereจะ represent 1 molecule. That means the top and the bottom sides. So next we consider, I shall call the self-doped molecular multi-insulate. So I consider this band splitting is large, but not so large. So there is a small overlap between the bonding and anti-bonding in this case. So what happened in this case, I will have such kind of picture. Majority side will be in the lower band, okay. And I consider also there's such a kind that we call the on-site, this doubleon. Doubleon means the anti-bonding and the bonding, both states are occupied, but with parallel spin. But this is an interesting point. If this side, okay, can be written in terms of this side, actually the same. Okay, so that is the same as just the one spin up in the top layer and the one spin up on the bottom layer. That causes no cooling effect. Okay, note that here is the molecule. This the real system is this top and the bottom. So that state actually does not cause any cooling effect. So what I found here is the lower Hubbard band. I can have a hole and a bonding state and the anti-bonding state with a small number and double. The reason I mix with small anti-bonding state because you have this to gain kinetic energy. Okay. So then that model actually the red ones anti-bonding state can move with the same speed like here, okay, freely. So this is a very weakly correlated system. And also the Hamiltonian can be written into bonding, anti-bonding, and the interaction part. And the bonding part is the blue part, okay. It's described by this projected TJ Hamiltonian. And that anti-bonding part, actually it's a diluted or weakly correlated system similar to the free electron. So that means in this case, I have so-called self-doped molecular multi-insulate. If the two bands, okay, split quite large, but not too large, still some overlap with these. And actually, I shall argue that what experiment discovered lanthanum 3, nickel 203, nickel 027 actually is just similar to this case with a little bit of complication and detail. So this is the cartoon slides. At the left side, it's I have a usual single band, and in the Coulomb, if Coulomb on-site repulsion is large, so I have a lower Hubbard band and upper Hubbard. If a lower Hubbard band is completely occupied, then I have a multi-insulate. Okay, in the square lattice case, I have a spin 1/2 Heisenberg model. Then if I consider like a molecular case, I have anti-bonding and the bonding already. Okay, so each bonding and anti-bonding, because of U, can have this the upper Hubbard band and lower Hubbard band. So what I draw here is I have a lower Hubbard band for bonding, lower Hubbard band for anti-bonding, and the upper Hubbard band for bonding and anti-bonding is 4 states because of the cooling. Okay, so that is also the molecular multi-insulator with doping is 1/4. This is doping is 1/2. And this is the right side is self-doped molecular multi-insulator. I still have that, but the spreading of the two bands is not so large. And at the large U limit, I have such kind of things. That means these two lower Hubbard band will have some overlap. Okay, so the red part basically serves the hole for the blue ones to move. And I shall argue below that that the material for the double layer nickelate actually is similar to that with the more complication. These blue ones actually will be discovered 2 orbits. Okay, and here is a single band orbit. So this is electronic structure again. Okay, and if I do this analysis, then I have these 2 relevant this EG orbital. Okay, with the dg square is lower, dx square minus y square slightly above. Remember that I have nickel actually is 2 plus 5 plus, okay, for each one. Here, for the 2 nickel, this molecular, I have 3 electrons. on this EG state, okay, for 2 nickel sites. And the double layer we're splitting, and for this the Z orbitals, I have a symmetric and antisymmetric. The splitting is large. For this orbital, there's a splitting relatively much smaller than this. The reason is this oxygen between these 2 nickels is PZ, okay, very strong bonding on between for the top and the bottom nickel. These 3D square term. So that is the analysis. So we can argue that this one, of course, you have 3 electrons, 2 will occupy this. So we leave 1 such EG electrons in this molecule, okay, for these 3 orbitals. So if I consider the next simplest case, this orbital is well above. So I have 1 electron for these 2 orbitals. Okay, so that's the case. And that 2 orbital Hamiltonia, and it can be written in the large U limit, it can be written in such kind of form. It's a little bit complicated, but well studied many years ago by Chomsky and by Castanelli. Okay. And if I set Henslow coupling vanishes, reduced to this form. Okay. And so essentially, this is a multi-insulator, but with 2 orbitals. Okay, it's a spin 1/2, and the orbital should spin 1/2 distance. So, more interesting case is this symmetric. That's dx square minus y square orbital is not so far away from it, because the splitting for this dx square minus y square is not so long. In this case, we have what is similar to what I call the self-doped multi-insulator. Here, the only thing is I have 2 different orbitals, okay, the blue ones and the green ones. And the blue ones represent the dx square minus y square, which we may have, may combine with this, the red ones, okay. These square, that's the green ones, the bonding state is totally occupied. So you can only have this anti-symmetric case. So in this case, I have in that low energy helped space without costing any U, I allow in such a kind of systems. Okay, so you have anti-symmetric. Okay, this for the blue ones, the x orbital, and for z orbital, and also you have this symmetric for the x orbital. Okay, you have double answer here. So the Hamiltonia can be written in terms of 3 parts: H1, H2, H mixed in term. Okay, and for the symmetric part, this is probably it's very close to 3 electrons because correlation is weak. The most interesting part is for the anti-symmetric band part. Is X and Z, they mix each other. So that has 2 parts. One is the kinetic energy, because now they have holes, they can move around, okay, and they have a spin, and the generalized spin-spin interaction means depending on orbitals. So how much time I have, the chair? 5 minutes. Okay, that's probably good enough. So here I just try a little bit of some complication. You know, just some may move freely. Okay, some technique detail. Okay, so basic information I try to address is this H12, the interaction of this the red part with the green and the blue part. Okay, it's a very weak. Maybe we can drop it out. Okay, we may focus on this H2 part. Describe that can be moving. Okay, also there's a spin correlation. And And that just to show you some, we look at in superconductivity instability. Okay, you can see the pairing form like this. Now, let me, because the two orbital model is quite complicated. Okay, so we want to take a simplified version from the band picture, just ignore the band, the two orbitals. Okay, we'll come back to that point. So the simple band will give us this 4-band, okay? And if you solve this problem, you have this beta band and alpha band, okay, like the blue ones and this. And this alpha band is inside, actually is similar to what I mentioned, is the red ones, which is almost free, okay? The blue ones in the calculation actually shows the combination of the two orbitals. But let's forget about this orbital, we found this band, okay. So we may just try to fit this beta band by a tie binding model, okay. So we can consider this T prime, T double prime fitting. This is not so good, but it's not too bad. It's red ones. Okay. Then we end up with a so-called T-J model. Okay. T means this beta band hopping, and the J means the spin-spin interaction of this blue band. Okay. Remember that here, the site is just a molecule consisting of 2 nickel sites, with one on top and one on bottom layer. Okay, so that model shows the D-wave superconductivity from the beta band. The alpha band is basically, it's a free electron, not much correlation, does not generate superconductivity much. Okay, that the simplified version actually was taken by us, I think, published in Chinese Physical Letters. So more complicated things, instead of showing you, a lot of parameters which we are still working on, I just like to make a few just comments. Chemical doping would increase TC experimentally, okay. And the partial replacement lantern of valence 3 plus by like a 2 plus electron strengthening, okay, should reduce electrons on the nickel side, which may enhance doping effect to increase TC. So that is a possibility we would suggest experiment colleague to do. The other is the importance of the inner apical oxygen, because the series and the similarity with the cuprate, okay, for the doped or self-doped MOT insulator, it's closely related to this inner apical oxygen to bond the top and the bottom nickel side. So if missing of inner apical oxygen would severely suppress superconductivity. And experimentally, they report this, the inner apical oxygen is terribly important. If a lot of missing, they don't get a superconductor. Okay. And we also could address the pressure dependence. We consider that because the pressure, first lower pressure is to have structure phase knowledge. This is too complicated for us. And so we may consider just within the high pressure phase, we further increase the pressure. Okay. Experiment TC actually decreases. Okay. If we further increase. And in the theory, this is just parameterized by strong anti-bonding orbital local energy. Okay. That's relative to another orbital energy. And qualitatively, we may argue this would not favor the pairing. And how to do mean field theory for the two orbitals. That formalism has been, I think, formulated. We can apply so-called renormalized mean field theory to use a set of renormalization constant to repress the constraint we impose, because the whole idea of this TJ model, Hubbard model here is the constraint. We do not allow two electrons on one side because it costs huge energy, coupled U. Okay, so we can use this set of parameters to repress the constraint and to introduce the hopping mean field and also spin singlet pairing mean field. Here we assume it's spin singlet, but we can also study other possible, triple pairing disk. So we did some simple cases. This is just a special case with only spin-spin interaction. Okay. Ignore the orbital part. Okay. And but I had two orbitals here. So this is what I get the mean field. Okay. The non-zero mean field of delta implies superconductivity. So this is for two atomic level of the anti-symmetric to be the same. I can increase this Z orbital has a low energy, then it looks probably better in this case. Okay. So I have larger delta in this case. But this is just to show you, we start to work on that. Okay. And finally, I like to mention briefly the other people's work. There are many calculations for this double layer compound. Okay, but weak coupling calculation actually reaches they all reach the same conclusion. Okay, what I show you is the weak coupling approach carried out by Harold Hwang. Okay, in Nanjing University, he used singular mode functional RG. Okay. So what they did is just the instability, like this for this compound. Okay, and I'd like to mention that what the wave they found is pairing symmetry is S plus minus. We found it as a D wave. So all the weak coupling give you the S plus minus, and some of the strong coupling predict the D wave. So because of this discrepancy, probably we'd be careful about the pairing symmetry in experiment. Okay, finally we're. Okay, so I think my time is over, so I would like to give a very brief summary. I think try to convince you that the Nickelate age finally comes and also has some promising with, TC above 80 Kelvin. So that is really remarkable. Okay. And unfortunately, right now, we're at a very high pressure, which restrict a lot of experiment. But hopefully, the experiment people may be smart, to repress this high pressure by other methods. So my, I think a message is for Nickelate, for infinity Nickelate, this is similar to cuprate dope. That's the Mott insulate. For this high TC double layer Nickelate superconductivity, what I try to convince you is I have similar things, but here is the molecular Mott insulate. I have two sides from a molecule. Okay, so that means each side you have 1.5 nickel electrons. Okay, with one nickel complete field, half nickel, another nickel, half electron. So 1 electron per molecule. That gives us similar physics with the cuprate. The difference is in that cuprate is just one side of copper. Here is the two nickel side to form a molecule. Okay, I think I'll stop here. Thank you for your attention. So it's somehow I mismanaged. Let's see.
I think just the last slide is illustrative enough.
No, she wants to see the real things. This one, right?
You have the red and blue ones. They appear two different momentum.
Oh no, yeah, actually this is the real space.
Yeah, this is real space. In momentum space, if you look at
momentum space, because you just start something like Mach physics.
Yeah.
You just start from the local picture. If I start from the momentum picture, then the orbital probably does not play much role, as we already carried out. So this is more sophisticated. So these are the moment, these are in our real space. So I have this one, you are probably right. Yeah, this one actually just you have one orbital, one in this antisymmetry, one symmetry, but both the same orbital. If spin parallel each other, that means one on top, one on bottom. So that does not cause cooling energy.
yeah. So let's think about it that one then. Okay, and then it's a double on. So can I just condense that instead of going to projecting on the single band? Can I, is there some limit where I can just condense the double on and become a superconductor?
Oh, that would be too much for us. I think you want to consider double on. Double on, here, for instance, this double on, okay, can move that here. The red one can move here free.
That's right.
Yeah.
Without
So
it.
motion is still one half carrier.
And that disturbs the superconducting density.
Yeah, it does not get become.
Right.
We thought about that, but
Okay. That's
not
really
good.
cool.
Okay, thanks a lot. I think we need to stop it there. So yeah.